Let's look at the force on a current carrying conductor in a uniform magnetic field. We have seen that the current carrying conductor sets up its own magnetic field. If such a conductor is placed in an external magnetic field, the magnetic field of the conductor will interact with the external magnetic field, and as a result of which the conductor may experience a force. To demonstrate this effect, consider a rod of copper capable of moving on a pair of copper rails. The whole arrangement is placed in between the pulled pieces of horseshoe magnet so that the copper rod is subjected to a magnetic field directed vertically upwards. When a current is passed through the copper rod from the battery, the rod moves on the rails. The relative direction of the current, magnetic field, and the motion of the conductor are shown in figure 14.3. It can be seen that the force on the conductor is always at the right angles to the plane which contains the rod and the direction of the magnetic field. The magnitude of the force depends upon the following factors. Number 1, the force F is directly proportional to sine alpha, where alpha is the angle between the conductor and the field. From this, it follows that the force is 0 if the rod is placed parallel to the field and is maximum when the conductor is placed at right angles to the field. F is directly proportional to sine alpha. Number 2, the force F is directly proportional to current I flowing through the conductor. The more the current, greater is the force. F is directly proportional to I. Number 3, the force F is directly proportional to the length of the conductor inside the magnetic field. F is directly proportional to L. Number 4, the force F is directly proportional to the strength of the applied magnetic field. The stronger the field, the greater is the force. If we represent the strength of the field by B, then F is directly proportional to B. And combining all the factors is F is directly proportional to ILB sine theta. Or F is equal to K ILB sine theta, where K is the constant of proportionality. If we follow SI units, the value of K is 1. Thus, in SI units, F is equal to ILB sine theta. Equation 14.1 provides a definition for the strength of magnetic field. If I is equal to 1 ampere, L is equal to 1 meter, and alpha is equal to 90 degrees, then F is equal to B. Thus, B, the strength of the magnetic field, which is also known as the magnetic induction, is defined as a force acting on 1 meter length of the conductor placed at right angle to the magnetic field when 1 ampere current is passing through it. The SI units of the B is Tesla. A magnetic field is said to have a strength 1 Tesla if it exerts a force of 1 Newton on 1 meter length of the conductor placed at right angles to the field when a current of 1 ampere passes through the conductor. Thus, 1 Tesla is equal to 1 Newton ampere inverse meter inverse. It can be seen that the force on a current carrying conductor is given both in magnitude and direction by the following equation: F is equal to ILB, where the vector L is the direction of the current flow, the magnitude of the vector IL and to B is ILB sine theta, where alpha is the angle between the vector L and B. This gives the magnitude of the force. The direction of the force F is also correctly given by the right hand rule of the cross product of vectors of L and B. For example, rotate L to coincide with B through the smaller angle. Curl the fingers of the right hand in the direction of rotation. The thumb points in the direction of force. In some situation, the direction of the force is conveniently determined by applying the following rule. Consider a straight current-carrying conductor held at right angle to a magnetic field such that the current flows out of the plane of paper. For example, towards the reader as shown in the figure 14.4. It is customary to represent current flowing towards the reader by a symbol dot and current flowing away from him by a cross. In order to find the direction of force, consider the lines of force. The two fields tend to reinforce each other on the left-hand side of the conductor and cancel each other on the right-hand side of it. The conductor tends to move towards the weaker part of the field. For example, the force on the conductor will be directed towards the right in a direction at right angles to both the conductor and the magnetic field. This rule is often referred as the extension of right-hand rule. It can be seen that the direction of the force is the same as given by the direction of the vector L into B.